the director of WNCG, as most of you know, but I'll just introduce him for people here who are new. So Robert Heath received his PhD at Stanford University, and he's a full professor here. He's also CEO of MIMO Wireless Incorporated, something I did not know. And he has won many awards, including the Signal Processing Magazine Best Paper Award and the 2013 Signal Processing Society Best Paper Award. And he's also a fellow of the IEEE. So he will be talking to us about millimeter MIMO. And Robert, there you go.
All right, thank you. So yes, it's great to give the first of this semester WNCG seminar series. We have had about 11 years of seminars now. And I figured since I'm going to give the WNCG introduction later at noon, that I might as well also talk to you all at 11 and provide, some technical introduction as well to some of the things that we do here, as well as, offering cookies and pizza as bribery to get you to actually come to my talk. For the 4 of you that are taking my class right now, you get the joke. Okay, so this presentation is on millimeter wave MIMO communication, and this is really intended to be a high-level presentation. I confess I have just one gratuitous equation later in the end. So really what this is about is telling you a little bit about the potential for MIMO communication at millimeter wave frequencies, and talk about some of the challenges and give you a little bit of background on why this is such an interesting topic, why so many of us are really looking at this. Now I want to start off with some context, and oh wow, this quality is not very good here. I'll explain what this is up here. So this talk came from a workshop that I co-organized on August 1st for my PhD advisor, Rogaswamy Paulraj. And this was in honor of his 70th birthday. And so I gave a talk here, which is, you can't quite see it because of the resolution issue here. And so I thought I would kick off the presentation just with some background about my advisor. Many of you have heard of him, but he really is, an amazing person and was a real inspiration for me. A little bit of background about him. He joined the Indian Navy at 15 and did his bachelor's in one of the, essentially like a naval college. And he worked in the Navy for a total of 30 years before even becoming a professor. He did his master's and PhD from IIT Delhi. And there's sort of an interesting story here that it turns out the college that he went to wasn't considered good enough for him to even get into IIT Delhi, but it was only because of one of the professors there saw his potential, and they really encouraged the Navy to let him take some leave and apply. And one of his main contributions that he's known for in India is developing the main shallow water sonar technology that is actually still in use in the Indian Navy. And he developed this technology at a time when there was a conflict with Pakistan, was what first created the need for the technology. And this was a time where India had just gotten independence and didn't have any sonar of their own. And so he came in and developed this sonar using, interestingly enough, multiple sensor technology, beamforming, and so on, things that he's been working on throughout his career, and took that and developed a world-class sonar system. And it's still in use today, and it was actually considered the best shallow water sonar until recently, actually, around the world. That's one of the interesting things he did in his career. He's done a whole bunch of things. Towards the end of his career, right after he retired, he founded something called the Center for Development of Advanced Computing, built the first parallel computer in India. And then after this, he left and joined Stanford at the ripe young age of 48. So I'm not 48 yet. That was really interesting here. And he joined as a research professor. So this is a little bit different. Most of the professors you see here, we came as assistant professors, and we teach and we do research and we supervise students. And he came in, without any teaching responsibility, but he had to raise his entire salary because research professor doesn't get any money from the university. So he came in, raised all of his salary here, and started a research group that lasted about 20 years here. Some of the notable awards he received. One of the reasons that we put this workshop together for him was he received the Marconi Prize this year, which is essentially the top award in communications. It's kind of like the closest we have to a Nobel Prize. Only pays $100,000 instead of $700, but that's still a reasonable amount of money, at least for me. He's received the IEEE Alexander Graham Bell Medal, which is a very prestigious medal, the Padma Bhushan Award, which is really like the highest civilian national award in India. And he's also a member of the U.S. National Academy of Engineering, as well as several other national academies here. So he's received like a lot of awards for his work. Now, one of the things I found really interesting, so when I was with him, I helped him start this first company called IOSpan Wireless. And it was, we developed tons of cool technology. You know, I learned all kinds of interesting things. Like he taught me how to solder correctly for the first time, which was pretty amazing. A, that I didn't know how to solder, and B, that he knew how to solder and he could show me. And that company was a great experience. It was a complete failure. The patents were sold and at a huge discount of what they were inevitably in the end worth. He started a second company doing basically the same thing called Beam Wireless, and that was developed what essentially became WiMAX and also the core technology in LTE. That company was sold to Beam to Broadcom. And now I just found out at 70 he has started a third company. And he's put together a similar team as before, and I think he told me the name, and I confess I forgot. But he's doing yet another wireless company. So this is pretty amazing. Anyway, so I just wanted to tell you a little bit about him, and it was a great honor to give a lecture at his workshop. And then when I gave the lecture, I didn't tell you what I just told you right now, because of course this was all about him. But I told him just a little bit about my group and the current students and the past students and the these are his grad students, and I was trying to actually track his great grad students, which would be my grad students. So we, rounded up another 24 of them here, and some of them actually are becoming professors. So we'll keep, pushing the legacy down here. And of course, these are all your, alumni as well, people that you can interact with and connect with as well. Okay, with that, I'll get into the motivation for the talk today. So this is really just the gratuitous motivation that appears in any talk of millimeter wave communication. This is 2 slices from the FCC's spectrum chart. This is a document you can download and print off. You can see it as a big poster. And what this is these are different frequencies here. And these are channels, and what you can't read here is the different kinds of allocations. So some of these are allocated for mobile services or fixed wireless or navigation or military or some other unspecified function. And what you see is from 300 megahertz to 3 gigahertz. Over here there's where Wi-Fi is, cellular is. A huge amount of congestion here. And these little channels here are not all that big. 80 megahertz at Wi-Fi, cellular in little chunks of 10 or 20 megahertz. And the way this FCC chart works is it's presented on the log scale. So this is 300 to 3 gigahertz. And if you go a couple slices down, you'll see the piece from 30 to 300 gigahertz. And so it turns out that because this is on a log scale, this is starting at 30 gigahertz, that all this spectrum here fits in only this little piece here at millimeter wave. And because this is log, this right here actually is only just a little piece there. So the real motivation for thinking about using millimeter wave carrier frequencies instead of lower frequencies is just that there's the potential to have channels with much larger bandwidths. So here, maximum sizes of these channelizations here are, on the order of 80 or 100 megahertz at best over here. I mean, there's channelizations as small as a few kilohertz down here, well, below 300 megahertz. So it's really just about the potential for getting very high bandwidth communication channels. Now, one thing to note is that look at all the colored blocks here. Millimeter wave is also used by many different services. I'm not saying that the millimeter wave is a new frontier where nothing is operating. There are all kinds of services at millimeter wave as well. But it turns out that many of these services actually are not widely used. So there's a lot of spectrum that's actually owned by people, and they're not really deploying anything on it. So there's a lot of opportunities here. Now, one of the big pushbacks when we talk about millimeter wave is a lot for consumer applications is that, this is going to be too expensive. It's based on these, fancy semiconductor technologies. It'll never be cost efficient in practice. Well, what's happening right now is and I'll tell you more about this later in the talk, but millimeter wave is coming to us in huge volumes at wireless LAN and for HDTV wireless connections here. So consumer products are already being shipped now and in the quantities of millions and are likely reach billions in the next couple of years. And that's at the specific unlicensed band of 60 gigahertz. So the technology is actually there now. And the final point I want to make is just that millimeter wave is not something that's incredibly new. In fact, it has its origins right at the beginning of wireless itself. Some of the first wireless experiments were done at millimeter wave. Bose in India and Lebedew in Russia both did experiments with millimeter wave in 1895. These were experiments showing the existence of propagation of waves and so on here. So millimeter wave, it's a technology that's been around. Now the main kind of motivation and connection between millimeter wave and MIMO is as follows here. So this is something, again, that's in every millimeter wave presentation, but basically if we look at a millimeter wave, a standard communication system, you've got an isotropic radiator, and you've got a receive antenna, and you're using, like, say, a standard receive antenna as a function of the wavelength, like a dipole antenna. So as you go into higher wavelength, what happens is the amount of surface area that you have, so this is like a low frequency antenna, and this is a high frequency antenna. So as you increase the frequency, the antennas get smaller, optimal like antenna size, and so what happens is you collect less power. And so this leads to this general belief that, this comes from the free space equation, that the smaller the wavelength, the smaller the received power. And this, of course, is exactly true if the receive antenna is scaling as we've described here with wavelength, which is a reasonable assumption based on how we make antennas. But what happens is if you can not decrease the size of the antenna, you keep the size of the antenna constant, you're going to integrate and collect exactly the same amount of power as you would have collected. And so how you can do that is essentially using the transmit and receive array gain here. So let me go back here. Let's see. All right. So effectively, if we can increase the aperture size here, we can collect the same amount of energy. And then, in fact, what we can do is we can cancel out this dependence on wavelength. Because if the aperture size is constant no matter what the wavelength, there's no dependence on wavelength here. So by having a large aperture, you can communicate, in theory, exactly the same as at a lower frequency. It becomes frequency independent. Now, another issue at millimeter wave is that the noise bandwidth is larger. The reason is that we want to use wide bands. We want to use 500 megahertz or a gigahertz or 2 gigahertz channels instead of 5 or 10 megahertz channels. Noise power spectral density being constant, when we multiply that by the bandwidth, we get a larger power. And we can't necessarily transmit more power in millimeter wave. We're still going to transmit, the order of watts of power, or if not milliwatts. And so we have to overcome this additional noise power here. And the way we can do that is by having a gain at the transmitter and gain at the receiver. So we can have additional gain turn here that can improve our received power and help us overcome the noise power here. Now, the natural question then is, how do we actually do that? How do we get gain at the transmitter and receiver? And the way we do this is through the use of antenna arrays, adaptive antennas. And so by collecting a whole bunch of antenna elements together and co-phasing their signals, you can create effectively directional antennas that have a large amount of gain and have reduced side lobes here. And this essentially forms the connection to MIMO communication. So we're going to use, an array of antennas at the transmitter, an array of antennas at the receiver, and we're going to exploit this array gain to overcome the effects of frequency dependence, overcome the noise power, and maybe to get even more gain. Now, this is like an overview of what are the challenges in doing things at millimeter wave. Because if you're studying digital communication, right? Where does the carrier frequency appear when you take digital communication class? It appears in like lecture 2, and there's some discussion about complex baseband model, and then the carrier frequency disappears and you never see it again the rest of class, right? Because we do everything at the baseband equivalent. So there's this temptation to say that, well, information theory, you never see the carrier there. All that stuff is carrier independent. And to some extent it's true, but you have to be very, very careful about the models. And so theory is actually important at millimeter wave here, and the fact that we're using millimeter wave does impact the theory through the different assumptions about the hardware, the propagation channel, and the constraints. So for example here, compared with a conventional MIMO communication system, in the propagation channel is different. There's not nearly as many reflectors as in lower frequencies. There's not what we call rich scattering, which is a MIMO concept where you have paths coming in from all directions. Not so much of that. Mobility becomes much more important. It's harder to design systems where we neglect mobility. Orientation becomes huge. So the actual, if you're using a directional antenna and you move your hand just slightly, you may have to retrain that entire antenna here, and that becomes a real big source of overhead. That's not really very important at lower frequencies. So that's like something about the channel. It's also hard to design efficient antennas. There's a lot of loss. The geometries of the antennas can play a role. Now, what about the hardware? Well, the hardware processing, there's a lot of power consumed when we do things with wide bandwidths and also at high frequencies. And so there's going to be additional constraints. Like, for example, the analog processing may take a lot of power. The joint processing may take power. We may use poor quality RF. We may have low gain. There may be nonlinearity issues. There may be additional quantization depending on how you do the phase shifting, extra insertion loss, and a huge penalty here for mixed signal power consumption. Operating gigasample per second ADCs, if we want to operate 64 of them, each of them takes a couple watts, that's 200 watts right there. And then that's in your phone, you would burn your hand. That's like touching the old incandescent style light bulb and holding it. That's only 100 watt. So that's, so it's infeasible here. So these things create constraints, and all of this is going to influence, the resulting theory here. So this is why millimeter wave is not just something for circuits and implementation. There's actually theory as well here. And then when you take all these different issues here and you multiply out by the fact that these millimeter wave systems may use anywhere from 8 to 256 antennas or more, you multiply the complexity and the consumption and the difficulty of all the processing here by that number. Now let me say a few words about the propagation channel. So this is one of the main places where millimeter wave and its low frequency counterparts differ quite a bit. So what I've done here is I've put together a table. Now this is a table that I synthesized from a lot of sources. Channel measurements are, they vary all over the place. So I'm trying to give you just like some high level insights into some of the different parameters. And this is like the low frequency Wi-Fi or cellular. This is a high frequency millimeter wave Wi-Fi, high frequency millimeter wave 5G cellular Wi-Fi here. So these parameters here correspond to measurements in the 60 gigahertz unlicensed band, and these are in either 28, 38, or 71 gigahertz. And then these are at 900, 1.8, or 2.4 gigahertz here. So some of the things we see, these are just parameters of the systems that, the number of antennas at the base station in conventional cellular is up to 8, and the handset is 1 or 2 typically, although it can support more. Millimeter wave Wi-Fi products that are sold right now have 16 or 32 antennas, both at the access point and on the handset or the laptop. And for cellular, that could even be bigger. Delay spreads. Delay spread actually goes down when you go up to millimeter wave. So here, like say up to 2 microseconds is typical. For millimeter wave, more like 40 nanoseconds. So this at first blush seems to be very good news. Because if you have less delay spread, maybe you don't need much equalization. That simplifies the receiver dramatically. But if we use a gigahertz of bandwidth, we have a 1 nanosecond symbol period. And so 40 nanoseconds turns into 40 taps of intersymbol interference. So actually the delay spread, even though it's smaller, is still potentially very high, and that does mean we might need equalization, a lot of equalization at millimeter wave. Keeping in mind you're doing that equalization on gigasamples per second. Angle spread's actually higher at millimeter wave. Angle spread is the variation, so if we have a path coming into this wall, and angle spread describes how much it spreads out. And at first I looked at this and I was like, that's not intuitive, it should be less. But actually, surfaces look rougher at small frequencies, and so they tend to disperse more. But also what happens is that a lot of that, because it's getting dispersed, the overall power also reduces quite a bit. And the other thing is the number of clusters. So the number of sort of dominant reflectors in lower frequencies typically up to 9, and a millimeter wave usually there's 1, 2, or 3. So in this room here, maybe there would be like a front wall and the side wall would be the dominant reflectors at all. And at low frequencies, you might get reflections off of you, off of the tables, off of everything here. So that means that there's a lot more sparsity in the propagation channel that could be exploited. The orientation sensitivity is much higher at millimeter wave because of this issues related to the sparsity in the channel and the tracking of the antennas. If you have only one dominant propagation path and you turn, where's your antenna going to point now? You need a path there. So that's another reason that the sensitivity is very large. Fading is not so important because there aren't as many paths coming in, so the Rayleigh model turns out to not be a very good fit. We of course have distance-dependent performance plus shadowing, but one of the differences that we've seen is that blockage is much more important at millimeter wave here. And so what I mean here is that, so before, if you made measurements outdoors, you would quantify errors in the distance-dependent path loss using, say, like a log-normal random variable. Basically, you just add a Gaussian error. And here, what we find is that there's a huge difference in the channels between if you're behind a building or in front of a building. And so just adding on a simple error term doesn't quantify that. In fact, the path loss characteristic fundamentally changes if you're in front or behind the building. So you might have like free space if you're in front of the building looking directly at the transmitter, but if you're behind the building, you might have a path loss exponent as much as 4.5 or 5, which is very much like non-line of sight, non-free space. So that varies a lot. And then you can even have mobile blockages, people reflect millimeter wave. And so, you can be walking by, you're streaming, like what if I was streaming my screen to the projector here and I walked in front of that path? Boom, we just lost gigabits per second there just because I, blocked the main path. So that's important. A lot of sparsity can be exploited at millimeter wave, and there's also potentially a lot more correlation. The reason I say spatial correlation is that not as many paths and much more closely spaced antennas. Okay, so now let's look at MIMO at millimeter wave. What role does MIMO have to play? Now I was putting this together and I thought, well, I should at least define what MIMO is in case there's some new students or people in the other areas that don't know what MIMO is here. So MIMO stands for multiple input, multiple output, and it is the communication paradigm we've been using for the most part the last 15 years, where you have multiple antennas at the transmitter, multiple antennas at the receiver, and you describe this propagation channel as a multiple input, multiple output system. So MIMO itself, the term has kind of evolved over the years, but now it really just refers to a system with multiple transmit and receive antennas, and there's all kinds of different signal processing that can be used. Different approaches at the transmitter, different approaches at the receiver, and all of those are under the MIMO umbrella. When you have these antennas, it changes the algorithms that you use, the signal processing, it changes how you design the transmit signals, it changes the performance of those algorithms, the rates you can achieve, the reliability, and it also changes the system design because it changes the trade-offs that you might want to make. And even though it's been around for a long time, I've had many students graduate that have worked on MIMO. I have this company, MIMO Wireless, and yet still it's a subject of intense research because it's one of the few ways of really getting additional degrees of freedom in a wireless system that you can use for capacity, for reliability, for dealing with interference. Now MIMO is widely deployed. Almost all of you have probably 2+ MIMO devices, or 2+ MIMO radios on your device with you right now, and you probably have 1 or 2 devices with you here. So wireless LAN has been using MIMO since about 2006. In cellular, it has been standardized since about then, but it's only made it in wide use in commercial products the last few years. And this is a forecast a couple years ago, which was that ABIR forecast 7.4 billion 11N devices in 2015. And 11N devices have to support 2-stream MIMO at minimum. So we're talking, if we add the cellular radios as well, there's probably right now somewhere between 5 and 10 billion MIMO-enabled radios in the world. And that number is just going to keep increasing. Now, let's look at MIMO at millimeter wave. So one of the big differences with these low frequencies and high frequencies is related to the power consumption of these mixed signal devices. Now, as I mentioned before, these especially the analog to digital converter can consume a lot of power, but also the RF chain can consume a lot of power. So the first millimeter wave commercial systems, the 11AD, WiGig, and wireless HD, all use this analog beamforming model, where instead of having each antenna connected to a complete baseband or mixed signal chain, RF, and then all the processing done in digital, everything is done in the analog domain here. So the radio here sees what looks like only one RF chain. And then this signal is then, same signal is sent on all these different antennas, but is phase shifted. Phase shifter is just a time delay, little delay element here. By controlling all of these phases, you can create different beam patterns, and you can steer the beam to different radios here. So analog beamforming is what we would call single stream MIMO communication, because I'm sending only one data stream. I'm not getting any of the spatial multiplexing gains from MIMO. It's really hard to extend this to multi-stream and multi-user.
This is to avoid multiple digital analog converters?
Yes,
okay. And
analog to digital converters, yeah. And generally just to have a reasonable low power solution.
And is it because of cost or power?
It's probably both, although I think it's more driven by power than cost. Because if you can make these small and in silicon, I mean, you can make a lot of them. They're not very expensive, but it's really more of a power issue. So there's a lot of interesting research though related to this technology here. I mean, there's how do you do the beamforming? How do you know where to point? How do you point your receiver? And so this is pretty exciting here. And this is also nice because this is the way beamforming was done 20 years ago. So even though this looks kind of new and exciting from my perspective, for people that have been in the field long enough, it's like, oh, I can't believe we're doing this again. Which is great because then we can rewrite all those old papers, change the terminology, and get another, publish another 100 papers. Don't quote me on that. Now, one of the exciting things that we've been developing a lot here at UT is this idea of hybrid beamforming. Now, it seems to me that limiting ourselves to 2 mixed signal devices, 2 analog to digital converters, is a bit extreme. So maybe we can have 4 or 8. Especially at the base station, you should be able to tolerate a little bit of extra power. So the hybrid beamforming model is where we have multiple output streams here. So it's like 2 streams here, each connected to an RF beamformer. So this would be that bank of phase shifters. And then each output gets summed on the antennas here. And so you can imagine sending 2 pieces of information, each on its own beam here. And this I would call second order spatial multiplexing. You can use this for supporting multiple data streams to one user or multiple users. And the idea works both at the transmitter and receiver. And it's kind of cool because what happens here is that all this receive processing, you have to do some sort of a joint optimization between what you do in analog and what you do in digital. And it creates a lot of complexity. And for example, I mean, how do you measure the channel? When you try to estimate the channel, you get the channel after, you get the channel here. So you have to, the combining and the beamforming are part of the channel. And so to configure them, they have to be somehow done at the same time as the estimation. And it's really complicated. But this approach is very powerful because with just 1 or 2 extra RF chains, you can get quite a bit better performance if the channel supports multiple paths. You can also support multiple users much more easily, which you can't do otherwise. And you can correct for analog limitations. Like for example, those phase shifters, they're not continuous value. They may have only 2 bits, so you can have only 4 possible phase shifts. It's not a lot, but you can do a very coarse phase shifting here, and you can fix that in the digital here. So that's the hybrid beamforming approach. Now, there's also a totally different approach, and this is something else that I've started working on in my group here, but people have been working on in the field. I have several references down here for the last 4 or 5 years. So another alternative is to say, well, the problem with the ADC is that we want gigasamples per second, and we want like 14 bits per sample. That's the problem. So what if we can reduce the resolution? And what's the smallest it could be that actually works? Well, 1 bit. So the 1-bit idea is where we're going to have a complete RF chain connected to a quadrature 1-bit analog to digital converter. This means that in phase and quadrature we each quantize with 1 bit. So it's a sign, all it is. Is it greater than 0 or less than 0? We spit that out. You can do this with almost negligible complexity and power consumption, but it changes the entire theory here because we're so used to treating the received signal as being continuous. But now fundamentally the received signal is basically is binary, 0 or 1. So you can send a continuous, let's say, Gaussian signal here, but what you get out is something, you know, heavily quantized. And so the information theory, we have to look at continuous input, discrete output, or discrete input, discrete output channels instead of continuous input, continuous output. And it changes all the signal processing. I mean, how on earth do you estimate the channel if you have only 1 bit worth of information from each of those antennas? You know, it's very hard. And, you know, we're working on ways to solve that here. But, you know, so it changes the estimation, equalization, optimization, in both the theory and the practice here. So I think this is a, you know, very exciting also area of research here. Now there's other work as well. You know, I didn't want this to just be complete gratuitous advertising for my own group's work. So I wanted to tell you about another topic that's interesting, which is called line of sight MIMO. Now, one of the things about millimeter wave is that because of the reasons I just mentioned, there's not a lot of scattering clusters and scattering in the channel. And so, you know, even if we have 64 transmit and receive antennas, we can send maybe only a couple data streams between them, unless something very special happens. If you can make this distance small enough and this distance big enough to satisfy a certain property here, then effectively what will happen is that just by virtue of the difference in the path lengths here, this MIMO channel that you can create a channel that has very high rank. It's just, you know, it's going to be like a foot or 2 feet distance. But that's okay, because there are certain applications where that's fine. And so the demonstrations here have been claimed up to, you know, 300 gigabits per second. And the main application here is like chip to chip and then in data centers. So this is a picture of, you can't quite see the data center here, but these are all racks of computers, and all these colored things are just cables. There's cables all over the place. Cables fail, cables prevent proper cooling and circulation. You could use these line of sight millimeter wave MIMO techniques to get rid of all of these cables and allow high bandwidth communication links between every chassis. And because you can use all the elements for MIMO, instead of sending 1 or 2 data streams, we can send 64, 128. So we can get, you know, hundreds of gigabits per second or more in these close range links here. So this, I think, is another exciting area. I haven't seen so much in terms of industry realization of this yet, but there's been a number of good papers. And also I wanted to mention that, you know, all this works with polarization as well, and polarization is a very important source of diversity, and in fact is really critical because there's not as much scattering here. If you send information on a vertical polarization and your phone is misoriented, you're going to lose a lot of signal. In lower frequencies, there's enough scattering so that the polarizations get mixed. But here is not, and so polarization diversity is also a very, very important area here. Okay, so now I want to say something about consumer applications of millimeter wave MIMO. You know, I'm not really focusing on the expensive backhaul links, which are used right now. You know, I'm going to really focus on what is the potential at, you know, price points that we could all buy. So the chips have to cost like $5 for this to really be viable. And so then I started looking at this in terms of timeline here. Okay, well, what are the first millimeter wave consumer devices? Well, we had in around 2007 or so this wireless HD standard, and then 802.15.3c was being developed at the same time. This is a personal area networking standard that is HDMI cable replacement. So it's about 5 gigabits per second, raw data rate. It deals with uncompressed HDMI video, the first such solution of its kind. And that was developed in 2007. Products started shipping in 2009. You can buy them still. And then just about after that, 802.11ad started to be developed, and there was also in parallel an effort at WiGig. So wireless HD and WiGig are industry consortia. What happens a lot of times is that companies, for whatever reason, don't want to work through the standards process. So a few companies get together, they agree on their own standard, and then they push it in. And that's what happened here. So WiGig, a bunch of companies said, all right, this is what we're going to do. Let's design millimeter wave wireless LAN like this. And then they came back and pushed it in and said, hey, IEEE, how about you make this your standard? And, you know, magic happened, skipping many details here. So, and anyways, this product was standardized in, look, this is about 2010, 4 years ago. Chips started being developed and shipped around 2013. And you can now buy wireless LAN millimeter wave products in some stores right now. They're not widely deployed in phones yet, but there are chipsets that are sold specifically for phones. So we should see it in about another year or so here. And then now there's also a lot of interest in millimeter wave for cellular, and that, in best case, won't happen before 2020, and it might be like 2030, depending on how things go. Now, as you can probably guess here, there's more to the story, because that goes back to 1974. So what I found was really interesting, in fact, is that this is not really the first consumer application. In fact, the first real consumer application is in automotive radar. And there is work done as early as 1974, and you can already buy cars that have these different automotive radar systems installed. This ACC is adaptive cruise control, there's collision avoidance, there's millimeter wave for blind spot detection. So these are products, I mean, these are consumer in the sense that you as a consumer can buy a vehicle equipped with it. It's not cheap. You know, it's like maybe $1,500 or $3,000 to get this radar on your car, but it is something that is available broadly to consumers here. And so there's been products, and every manufacturer has its own different version that has been available now for 10 plus years. And I think there's a lot that we can learn by looking at what's happened in radar and then looking in parallel what's going on with the wireless communication.
When was the microwave oven?
I don't know. That's a microwave, man.
That's a microwave.
It's a millimeter wave talk. Relevant questions only. Yes?
Come on, I mean, when is the automotive radar?
No, microwave oven is, I mean, they were popular, in like 79. Yeah, hold on. Sorry about that.
Have they all been unlicensed microwave?
Well, this stuff here is all unlicensed, but this is actually their separate spectrum, and I have this on the next slide, but there's separate spectrum allocated for those different services. So they're not at the 60 gigahertz band. There's a separate 77, 78, and 81 gig bands.
But each manufacturer doesn't have exclusive access to a certain
No. No. Yeah, and so radar is, it is something where the different manufacturers with their different standards are sharing the same frequency band. But it's a different band than wireless LAN is operating in. Sanjay.
The power radiated by these things, what order are they, and are they sort of FCC Class C, Category C type TVs?
I think, I don't remember if I have it on the next slide or not, but it's still on the order of like watts. It's not really much more than the power outputs of these devices here. So it's, yeah, I thought that too, like, oh, maybe it's like 100 watts or something, but no, really, it's on the order of watts, if not less. And then as far as the FCC, I don't know the answer. So I'll tell you a little bit now about some of these different radar and then communication aspects here. So the main thing, punchline here is just that we in the WNCG are excited about wireless because we don't have R in the WNCG, right? There's no radar there, but the radar does predate the wireless, and people have been manufacturing products, and so we need to look at that, and there's potential synergies. So the automotive radar concept. This is summary here because at least I didn't know what radar does in cars because I don't own one of those fancy cars that has a radar at all. I'm lucky that my car actually has a radio. Now, there's three places here. There's automatic cruise control. This is the one where you're driving on the highway, you want to follow the car in front of you, and you don't want to have to keep slowing down and speeding up. So this is a long range, could be several hundred meters, but it's really just front and possibly back. You don't really care what's happening on the sides here. And that operates in an allocated band at 76 to 77, 600 megahertz bandwidth. Short range radar was operating at a lower frequency in 24 gigahertz, but that's actually being replaced by radios in 79 and 81. And then medium range is in 77 to 81. And so some of the different applications here. So, pre-crash, like someone's coming this way, and if you can detect that, the side airbags can be deployed faster. That saves a lot of lives. Parking aid, in case you don't know how to parallel park, can help you park. If you're making a turn and there's a bicycle there, they can detect that. There's someone in your blind spot. So there's a lot of different ways of using the radar here. Each of them is potentially a different device. So this automatic cruise control, this is in the front. And I was in the parking lot a couple days ago, not of the UT building, and I was looking at this Porsche, and it actually had one of the automotive radars in the front under the grille. That was pretty cool looking, but it would only work for this because it was like pointed in that direction here. So anyways, there's a lot of intriguing ways to use automotive radar. And I wanted to just show you some examples of how multiple antennas are incorporated, because all those radars do use antennas in some form. You need some ability to detect not only distance and range, but also location. And so this is Denso's electronically scanning phased array. This is a phased array technology. This is another digital beamforming phased array solution. This is a scanning radar. This is Toyota's CRDL radar. And then this is the Bosch long-range radar. This is the one that was in the Porsche here. And this, to give you an idea of the size, it's about that big. So it's not like in your phone kind of small, but it's not huge either. Fits sort of unobtrusively under the trunk there. And then this is another, and this actually uses a lens antenna. So this is not an array, but a steerable lens here. So multiple antennas has already been used there quite a lot. There's a lot of research issues associated with automotive radar. Not much being done in academia. I think there's an opportunity here. Work to be done on reduction in cost and weight. Autonomous driving, that's a huge area of interest. Self-driving cars. Well, how can self-driving cars drive without hitting other cars? Well, radar can be used to help avoid collisions surrounding field of view. There's multi-sensor fusion, joint vehicular communication radar. Dealing with interference, I mean, if everyone has a radar, they're going to interfere with each other. So you have to actually be able to deal with that without making stupid decisions like, oh, someone's crashing into me. Oh, no, it was just interference. Whoops, that's the problem. And so we're currently working on a couple of these problems here. The ones related to joint communication and radar. So we're trying to create waveforms that do both at the same time. And we're also looking at how you can communicate with other vehicles and use learning techniques to make inferences about stuff that's happening maybe many car lengths ahead. So using combinations of communication and radar to improve safety and efficiency. Now I want to say something about the development of 11AD. Even though wireless HD came before it, 11AD is going to be the consumer millimeter wave application that ships billion devices the soonest. So it started off in around 28. It was created end of 2008, around when the WiGig Alliance was created. And then WiGig essentially 1.0 became 802.11ad, draft 1.0 here, and then the usual sponsor ballot approval, et cetera here. One thing of noting here, WiGig essentially merged into Wi-Fi. So Wi-Fi is another industry consortium that is not at IEEE that certifies wireless LAN products. And so they basically acquired WiGig. So Wi-Fi will now also certify wireless LAN millimeter wave products. And then just other points of interest, Wirelocity chip was launched. Wirelocity now being just acquired by Qualcomm a few weeks ago. Products in Dell laptops already shipping. You can already buy, Itero is a local company making a chipset here. And this is another prediction that 2017 will have close to 2 billion 11AD devices here. So, and this is going to ramp up later this year. So basically, towards the end of this year and next year, almost every device is going to become packaged with an AC-AD dual capable chip. So a couple of the things that I find interesting about 11AD, this is just kind of in the category of random information here. There are 4 physical layers associated with 11AD. There's what they call the control physical layer, the single carrier physical layer, the OFDM physical layer, and the low power single carrier physical layer. So this is the default one. So this single carrier one is using something like a QAM, pulse amplitude modulated QAM waveform, just like we do in my wireless lab class, with a cyclic prefix, just like we do in my wireless lab class. So it's frequency domain equalization and single carrier. So this is different than what's done in cellular, because cellular is primarily using OFDMA. The access technique here is basically TDMA. You serve one user at a time. There's no multiple user access. Anything more sophisticated than that. There's an OFDM physical layer, but it's optional. And then the low power 5, this is interesting too. This one uses a form of constant envelope modulation. So it's a very power efficient kind of modulation. Doesn't have the capability to do much equalization or steer the antennas. That application is the kiosk where you're going and you go to Redbox and you put your phone there and you download the movie. It's only like a foot distance or something. And you have to point your phone at the right spot to get the data because there's no adaptive antenna in that one. But it could be very, very low power. So that's something that's intriguing here, that they had all these different PHYs, not just one, each to solve sort of a slightly different problem here. The single carrier is so popular because it has lower PAPR, and millimeter wave power amplifiers are not very efficient, especially in silicon on chip, so the power efficiency is very important. The other thing is that we don't need OFDMA because, if you're beamforming to one person in analog, unless there's two people standing in the same spot, that beam doesn't cover both of them. So if you're doing analog beamforming, OFDMA is kind of pointless unless everyone's like in the same place. So we don't need OFDMA, and then OFDM does have advantages in terms of over single carrier in terms of optimization of the communication link. But if there's not a lot of frequency selectivity, and any ways you can equalize with single carrier, the differences are not huge. And if you factor in the power consumption, it's a wash or it's a win for a single carrier. So where's MIMO? Well, MIMO, another intriguing thing about the standard, it doesn't tell you how many antennas to use because the standard itself is designed assuming beamforming with single stream. So it's left up to the provider to actually determine the number of antennas on their chip and to configure them appropriately. It has the mechanisms for configuring arrays, which I'll explain in the next slide, but it doesn't tell you to use 8 or 16. It does give parameters for certain common array geometries. And this is a Wilosity chip here, which is now Qualcomm, and they have 32 antennas. And that chip is about the size like my finger right here. That's the size of the array. So it's pretty small. The way the beamforming works is as follows here. So conventional MIMO system, we would send training more or less from each antenna, estimate the channel, compute the transmit beamformers or precoders, maybe send them back through a feedback channel, or we might use reciprocity. With beam training, the idea is that, well, instead of, I don't even have access to each antenna because I only send beamformed data. So what you do is the transmitter sends on this sector level sweep, it sends training data on each of 3 possible sectors here. So these are different beam patterns formed at the transmitter, and they have very low gain. Yes?
So why is this to minimize the number of RF chains?
The analog beamforming, or?
Why?
Yeah. I had a slide on that earlier, but basically analog beamforming is really to minimize the number of mixed signal chains and basically power consumption. Yeah. And further, it's not clear how much MIMO multiplexing gain there is to be had in these rich scattering channels. And so basically here, so you send data which is highly spread on each of these different sectors here. So you use spreading to overcome the fact there's not enough array gain. And then the receiver listens and figures out its own array configuration. And then, oh, by the way, the receiver and the transmitter, they can each take turns transmitting and receiving. Neither knows where to point its own beam, right? So this has to be done in both directions. Transmitters have to take turns sending on sector level, receivers take turns receiving, and then vice versa. And then you do this sweep, and each device figures out the preferred sector. And then there's a feedback phase, and then there's a beam refinement phase. And so there's essentially a way of progressively refining these different beam patterns until you get something that's narrower and narrower. And so instead of trying to train all the antennas, you just keep trying different possible beams in a smart way using, like, say, a binary search until you get one or a few that work well. And that's beam. This is not beak tracking, that's beam tracking. Although actually they do look like beaks, so it would work. And then over time, there's a periodic refinement here. So, as things are changing over time, instead of restarting the whole process, you can just start back by looking at a somewhat wider beam pattern and then narrowing it again here. So that's just something I found interesting about the single stream MIMO here. Now, there's a lot of research in millimeter wave wireless LAN to be done. One thing is really exciting. They have just started the successor to 11AD. It doesn't even have a set of initials yet, but they've started a working, task group, I think is the name. And so what they're looking at there is multi-stream instead of single streams. They're going to look at hybrid beamforming, and they're going to look at multi-user MIMO. So they're going to look at supporting multiple users, also with a hybrid architecture. So some of the things I talked about earlier is very likely to make it into this next generation wireless LAN. And if you go work for a company that's looking at wireless LAN, very likely you'll be working on that next product, because if that's being developed right now for the next 3 years, you know, and then implementations will start. So it's probably 5 years before we see it. So there's a lot of potential there. And then, you know, we're working on, I mean, pretty much everything I can think of that I can find students to work on, with the exception of packaging and antenna design. And I confess I am not an expert in packaging nor antenna design. So if anyone is here, I would be happy to work with you on this. Why I put that up at all? Because it's actually very hard to feed millimeter wave antennas. You know, at low frequencies, we just buy this coax. It loses like 0.1 dB a foot, whatever. You know, you have 10 feet of coax, you lose a couple dB. It doesn't matter. Very hard to create low loss coax. The best thing to do would be to have a waveguide, but waveguides are very rigid. And so most of the solutions for those arrays, most of the time they're on package, which means that the chip is made and this antenna basically is glued on top as part of the packaging around the chip. And then there's a lot of loss with the interconnect there. So you can't have like a millimeter wave array over there and a little cable and the processing over here, because you just can't make the cables that efficient, especially small cables. So that's why that's up there. So there's a lot of challenges here. I mean, this beam tracking, multi-stream, no implementations of that so far. I mean, just a couple, I should say. And you know, wireless LAN is 60 gigahertz, but there's unlicensed bands in 120, 180 gig and beyond. So why not use those bands too? So we're going to go up higher. There's the co-design of the algorithms, and then algorithms are robust. So what if, you know, this is my phone here, and I cover up. If the array is the size of my finger, and what if I put my finger on the array? What happens? Well, you get no signal because millimeter wave doesn't go through your finger, especially at 60 gigahertz. So there's a new notion of diversity. You probably have to have arrays on multiple sides of the phone. Or what if you have a big array and I block like half of the elements? A lot of, like, that would totally change how the beam looks if I just arbitrarily dropped 16 of the 32 elements. So robustness is also a big deal. So there's a lot of applications there. Now I'm going to wrap up with a bit of discussion about this new area, which is millimeter wave cellular. And you'll probably be seeing more talks on this. I mean, we have several students that will be qualifying and defending, talking about millimeter wave cellular. So you'll see a lot of this in subsequent seminars and talks here. So the main reason for millimeter wave for next generation 5G is just the same motivation I had on the first slide. It's really that there's not much spectrum over here at these very low frequencies. And there's a huge amount of spectrum at the high frequencies that could potentially be repurposed here. And we've done everything we can to do what we can do in a 20 megahertz channel. I mean, we've got, you know, this even 8x8 MIMO and multi-user MIMO and multi-cell MIMO and a super efficient coding. I mean, turbo and LDPC coding and adaptive modulation. And there's just no more spectral efficiencies to be had really in these links. And spectral efficiency gets multiplied by bandwidth. So if we can repurpose these other spectral bands, we can get several gigahertz of bandwidth. And even at relatively simple modulation techniques, you can get gigabits per second here. And so I think this is a really promising area. And this is maybe the frontier for 5G if spectrum can be made available. And if it can't, it'll be the frontier for 6G. There's basically no option, there's nowhere else to go but up. You know, unless the FCC decides to totally rethink how all spectrum is allocated and use some kind of complicated auction system, which I don't see happening in our lifetimes for all the spectrum. The only way we can go is up, and there's a whole bunch of incumbents that we can move here without much money. And so that's very promising there. Now, what would a millimeter wave 5G cellular network look like? I mean, would it look just like today? Well, it wouldn't because of the propagation conditions. So a millimeter wave base station probably will be smaller, won't serve such a large area. Maybe it will only serve 100 meters instead of a kilometer. And you can use millimeter wave for, you know, communication links. There's going to be you know, millimeter wave small cells, millimeter wave femtocells to serve indoor users. You might have millimeter wave used for backhaul. This is exciting. You don't need necessarily to wire up all of your base stations, because if you have very pointy directional beams, why not use those beams to send data from one base station to another? You save a lot of cost that way. Much of the operating costs for base stations are associated with backhaul. And you can use the same band even. So backhaul is important. You've got issues related to, you know, look here. I've got this phone, admittedly old style phone, is being served by 2 base stations at the same time. Why? Well, someone comes along, a truck comes over here, blocks this beam, still this beam can be used. So we're likely to see very dense deployments of infrastructure, partially for diversity purposes here, and partially for better coverage. We're going to see device to device. I mean, if I have a 4 gig movie file that I have acquired completely legally on the internet and I want to give it to you, why not use millimeter wave to transfer it there? Instead of downloading all these poor resolution versions, we can get the high-res versions and share the HD videos with our friends. And that can happen with low density links. And I don't want to say that the low frequency is, we're going to discard it. We're going to still use it. And it may be vital, because it may be that we use the low frequencies to control all of these other millimeter wave links. Because of the issues related to blockage and non-line of sight. So for example, if you're indoors, a lot of times millimeter wave, depending on the building, will penetrate some or not at all. Most of the time, not at all. But microwave does penetrate. So you could switch to a microwave frequency when you go indoors, or you could offload to millimeter wave wireless LAN, or you could find a millimeter wave femtocell, and this could all be coordinated through the low frequency conventional cellular link. So last, I'm going to highlight just a couple things that we've done recently, and this is mostly work from Tin Yang, who's in the audience here. This is our initial analysis of the millimeter wave cellular capacity. What we wanted to do is we wanted to use this stochastic geometry framework that Jeff Andrews and Francois Bocelli have been pioneering, and we wanted to incorporate the features of millimeter wave into that model. And like many of you know, who've taken Professor Bocelli's class, when you tweak things a little bit in stochastic geometry, everything, in my opinion, seems to break completely, or the equations go from being 1 line to 50 lines, if you can solve them at all. So we're trying to add enough complexity that it's interesting, and yet still get some intuition out of it. And so we erred a little bit more on the side of intuition and some approximations here. So the two things that we incorporated, and I think these in the first cut are the most important. The first is the directional antenna. If you have no directional antenna, you're not doing millimeter wave. You have to have directionality. At the same time, it's very hard to look at a complicated beam pattern and look at all these different issues related to estimation. So we approximate a directional antenna like this here. There's a main lobe with a certain gain m. There's a beam width theta, and a back lobe gain little m. Now, some of you theoreticians are thinking, why is that back lobe gain m, little m there? That should be 0. Ideal antennas, right? No, it's not. And this gain, this may be 20 dB difference, and you may think that's huge. That's not that big. So there's a lot of interference to be had from the back lobe here. That's the message here. And the way we approximated it is roughly as follows here. So you can see our back lobe is a bit pessimistic, and our main lobe is tiny bit optimistic. So we neglect essentially this effect here, and we neglect that there's a whole bunch of nulls in the back. So I think it's actually a pretty reasonable model for directional beamforming, not for the more sophisticated beamforming approaches. And then to model the effect of blockage, we use this prior work we did on modeling urban environments using random shape theory to compute essentially a probability that a user is blocked. And so we have a model for dropping buildings with a certain density with certain length and width distributions here, and making some assumptions. You can show that the probability that a link is unblocked is exponential, e to the minus beta of r, where r is the link length, and beta is a function of the density and the size of the buildings. Essentially, the bigger the buildings you have and the more dense the buildings are, the more quickly that probability decays. So if you're in a very dense urban area, the chance that your line of sight is very small. So that's the way that we incorporate blockage, instead of having some kind of a log normal random variable here. And then what we do is we use this blockage model to apply different path loss laws to line of sight or non-line of sight. And so this is my one gratuitous equation that we got, where there's an approximation here. But the net of it is we could find a reasonable approximation of the SINR coverage capacity, making several assumptions, and I'll now just give you the effects, basically the results here. So some of the things we've been able to do have been study the coverage probability. So this is an SINR threshold, and this is coverage probability here. So basically you'd like to be up here. And this is for a certain density of buildings, which corresponds to the UT campus. And this is basically adding more infrastructure. So this is like not many base stations, more base stations, a lot of base stations. And as you add base stations, the coverage probability goes from horrible, pretty horrible, to amazing with enough density. And there's a relationship between the density of buildings and density of base stations. You need roughly twice as many base stations as buildings to get good performance. And then we also look at achievable rates here, where this is rate instead of SINR. And depending on the density here, so this is like, you can get with reasonable performance here, reasonable density, very, 400 or 500 megabits per second. And this is not in a very big bandwidth. This is comparing 20 megahertz microwave and 100 megahertz millimeter wave. So you can get high data rates reliably with enough density. This is just a final average rates comparison here. So this is low frequency single user MIMO. This is low frequency massive MIMO, which is another area of interest that I won't tell you about today. And these are the cell throughputs, the inner site distance, and the rates per area. And so what we see is, we go from, let's see, millimeter wave. This is single user with analog beamforming, so with one stream, one user per cell, 400 meters. We get about factor of 3x in terms of rates per area. But we use 5x more bandwidth. Whoops. But we go here, we increase the density. And now we're operating, see here, we're operating in that horrible coverage region because we're line of sight most of the time. With enough density, that's what I showed you previously, now you're line of sight most of the time, and the rate improvement is more than the 5x. And the reason it's more than 5x is that the rate is not just coming from the bandwidth, there's also a reduction in interference because of the beamforming. So we're creating a better interference environment and we're getting a higher bandwidth. So both of those come together to give us a much higher data rate. And everything I talked about single stream, but the work we've done on hybrid beamforming, it can also be applied. And with 2 users, we can actually get about a factor of 2 improvement of that. And this compares very favorably with massive MIMO, which is the state-of-the-art low-frequency technique that does quite well, but because it's operating in 20 megahertz of bandwidth, just can never get you to gigabits per second. Okay, so just to wrap up here, so millimeter wave has massive consumer potential, has massive potential for you all for research projects, for papers, for dissertations, for jobs, for startups. We're going to see 1.7 billion millimeter wave consumer devices in a couple years, if not sooner. And LAN is going to be the big first wide-scale deployment. You can buy the ones for the HDTV cable replacement, but they're just not widely sold. There's only a few million of those sold right now. And MIMO and millimeter wave, they work together because we have to have the antennas for millimeter wave. MIMO is all about antennas. Single stream is the de facto standard. Everything is going to multi-stream and multi-user in the next 4 or 5 years. But we have to do this research. We can't do it in isolation. I mean, we have to really understand the constraints to make everything relevant here. Okay, so that's it. Any final questions? Yes, so here, Jinshin.
Talking about millimeter wave cellular,
Yeah.
You just mentioned, for example, if we use 1 gigahertz millimeter wave channel, then the symbol period is 1 nanosecond. So if a user moves just like 3 meters, that amounts to 10 nanoseconds. So how can synchronization be done in that kind of scenario? And also you mentioned we want to do multiple base station access. As far as I know, according to the current TDD deployment, base stations are synchronized, but the synchronization error can be up to 3 microseconds. That amounts to 3,000 symbols. Yes. So my question is, how can synchronization be done in millimeter wave cellular?
Yeah, okay.
So I guess that's a good question. Now the synchronization problem, that's an important signal processing question. Most people don't work on synchronization anymore because it seems to be like a dead topic, even though it's in every device and it's pretty hard to do. Synchronization, first of all, the problem you mentioned about like moving 3 meters and that synchronization piece isn't that big of a deal because the question is how long it takes you to move that 3 meters, right? If it takes you 1 second, well, 1 billion symbols have gone by the time you get from point A to point B. And if we're using frames of length, 200 symbols, I mean, you've seen 100,000 frames go by. So the need for resynchronizing based on mobility, not such a critical issue in my opinion. I mean, it's important, but it has to be done. But things like retraining the equalizer, redoing the beams, all of that does have to be done. But if you're doing that on the seconds level, it's not a huge overhead in my opinion. Now that is one of the reasons that beams can't be too narrow. So we should not think about millimeter wave as shooting lasers, because any small perturbation, you have to refire your laser, and that will eat up all the overhead. So there is some trade-off there that has to be discovered in terms of beam width and what's really practical. So we're looking at that also. Now the point you bring up about multiple base stations is, it's perfect. I mean, you're right. I mean, just the propagation differences alone, let alone the difference in synchronization are a big deal. So what I see for multiple base station is, it's not necessarily that the base station both base stations are sending you the same data. And maybe that one is just is buffering the data, and should you send a NAC or I'm a blocked message, then it starts sending you data. So I'm kind of skeptical about it sending data at the same time, because if it arrives with the delay you said, you have a massive equalization problem, potentially. So, but these are basically good questions.
More of soft kind of?
I don't want to say it's kind of, to me it's like hard. It's not soft, because you're not necessarily getting data from both, but it's sort of a rapid switching. Because the blockage could just be someone walks in front of the main beam and then they walk away. So it's not going to be that I'm like handing off for a while. It just might be that temporarily I get data from there. And so constantly two base stations could be both trying to serve me, and there may be scheduling constraints. This base station's trying to serve other people, and so I don't know. I think it's a pretty interesting topic. So there's another question. Yeah.
Should we go for the stochastic channel formation, or should we go for deterministic? Because the number of reflectors and those type of things reduce in this new what you have done in microwave, like we have gone for stochastic.
Yeah. There are a lot of stochastic channel models for millimeter wave too. Basically, it's similar models, the parameters are different. So the angle spread is lower, but it's similar distribution like Laplacian or Gaussian angle spread, but 3 clusters instead of 10 clusters. So you still need stochastic models. I think they're still useful. And in fact, I think if you go for pure deterministic, you won't get enough variation in the signal, and you'll probably get a pessimistic result. In other words, it'll be too easy to actually equalize your signal. So you need that variation to make it work. All right, any final questions? All right, so the plan now is we're going to take like a 10-minute break, eat pizza, and then we'll come back for the second presentation.